Hello! This is a new chapter, and we are going to talk about Kirchhoff's law. Well, Kirchhoff's circuit law lie at the heart of circuit analysis. With the help of these laws and the equation for individual components like resistor, capacitor, and inductor, we have the basic tool to start analyzing circuits. So in this chapter, we will discuss about Kirchhoff's current and voltage law and how to employ them in circuit analysis. So let's get started. Alright, so before we get into more details, let's just give some credit to this German physicist Gustav Robert Kirchhoff, whose first research topic was on the conduction electricity. This research led to Kirchhoff formulating the laws of closed electric circuits in 1845, if I'm not mistaken. And these laws were eventually named after Kirchhoff and are now known as Kirchhoff's voltage and current laws. Since these laws apply to all electric circuits, understanding their fundamentals is very important in the understanding of how an electronic circuit functions. Alright, but what are Kirchhoff's laws exactly? Well, this Gustav Kirchhoff developed a pair of laws that deal with the conservation of current and energy within electrical circuits. You might ask yourself, okay, but what are these two laws are used for? Well, these laws help in calculating the electrical resistance of a complex network or impedance in case of AC, and the current flow in different streams of the network. In other words, Kirchhoff's laws are used to help us understand how current and voltage work within a circuit. If you hear about these two laws for the first time, it might probably scare you a little bit, but don't worry because they are really simple to apply once you understand them. So before we explain about these two laws, in this course we will talk only about the first law and in the next course about the second one. So before we get into what this law is about, we have to get familiar with some terms. We had this circuit here, right? And what do we see here? Some resistors, a battery, and that's all. But this image shows something that we didn't see before, and that is these connection dots are named as nodes. From this point to this point is considered a branch, and since this part of the circuit is closed, we can draw a loop inside it. Let's see if you understand what is node, branch, and loop. First of all, how many nodes does this circuit have? The first node is at point B, and the second one is at point E. You have probably observed that a node needs to have at least 3 connections, right? Now, how many branches do we have here? 3, right? The first branch is from point A to F, the second one is from B to B and E, and the third one is from point C and D. Now, how many loops can we form in this circuit? One loop is within A, B, E, and F, and the second loop is considered within B, C, D, and E. Alright, so now that we are familiar with these 3 terms, let's see what is Kirchhoff's first law about. So according to Kirchhoff's current law, the total current entering a junction or a node is equal to the currents leaving the node. And that's it. That's all you have to know about the first Kirchhoff's law. Currents entering the node equals to currents leaving the node. So in this figure, as you can see, the currents I1, I2, and I3 is entering the node and is considered positive. Likewise, the currents I4 and I5 exiting the node is considered negative in values. And this can be expressed in the form of the following equation. I1 plus I2 plus I3 minus I4 minus I5 equal to 0. Why don't we solve some exercises together to understand Kirchhoff's current law better? So here is an exercise for you. If a 3-way circuit junction has 2 wires with 2 amperes each entering, how much current is the third wire? Remember, the sum of currents entering a node is equal to the sum of current exiting a node. So we have 2 currents entering the node, and since they enter the node, they will be positive in sign, and we can add them up together. Since there's only one current exiting the node, the current on the third wire will be equal to the sum of the currents entering the node, which is equal to 4 amps. Alright, let's move on to the next exercise. The question is, if the current is 10 milliamps before the 2 resistors, what is the current after the resistors? We know that the total current entering a part of the circuit must be equal to the total current exiting, right? If this circuit doesn't branch with anything else, it will have the same current at every point. Remember that current doesn't change across resistors and batteries. The last exercise asks you to find the current before the circuit splits into 3 branches. So what's the current at this point of the circuit? Sum of the currents in is equal to the sum of currents out, right? We have only one current in and 3 currents out. So the input current is equal to 20 plus 40 plus 55 milliamps, and the final result is 115 milliamps. Kirchhoff's current law isn't that hard after all, isn't it?